the universal decision rule and confidence intervals. What is the universal decision rule? This is associated with the decision rule in step 6. What is a confidence interval? This will utilize the standard error we've discussed, only we'll be using the observed proportion rather than the null. And how do you use p-values and confidence intervals to answer a statistical question? Again, we have the 10 steps broken into 4 phases. State the question, decide how to answer the question, and then communicate the answer to the question. Our universal decision rule will be decided as choose the null hypothesis if our p-value is greater than alpha. We will choose the alternative hypothesis if our p-value is less than or equal to alpha. This is usually an alpha of 0.05. What that means, again, is we are comfortable with selecting the alternative 5% of the time when the null is really true. So we are comfortable with making the wrong decision in terms of the null being true, but choosing the alternative 5% of the time. We will choose the null hypothesis if our p-value is greater than alpha, indicating it is unlikely that our results are different from what we expected. Or we will choose our alternative hypothesis if our p-value is less than or equal to alpha, meaning that our observed results are highly unexpected. And that gives more evidence that the alternative is what we should believe. So how do we determine p-values? You can calculate your z-score and then go to a table such as those in the back of your textbook in Daniel and determine a p-value from there. This is very tedious. You have to be careful because there are tables that will give you the p-value associated with the null. They will give you the p-value associated with the alternative. So sometimes it will give you a 0.999 when what you really need is less than 0.0001. So we will in fact use a calculator, and in fact we'll actually start just using the software. But you still need to be careful that you know what p-value they're giving you, and this will become clear when we begin to use JUMP. We will have a calculator that you can use based on Excel. These figures look very similar to the theoretical distribution that we looked at for the simulation for ECMO. And in fact, this is the 3 options that we have for our null hypothesis. So equal to, which is in the bottom, less than or greater than. And this calculator will give you the p-value that is associated with any one of those tests. We will spend more time on this calculator in the next section. A calculation note, software or calculators may return a p-value as 0 or 0.00. This is not possible. If you'll notice, in these figures, the curved line never actually will touch the axis. This is what's called an asymptote. It is a calculus term. But what it really means is that no matter how small, even approaching infinity or negative infinity, the probability of observing a number that extreme still exists. So it is never a 0. You will then report a p less than 0.001 or a p less than 0.0001. Do not ever report a p-value of 1 or a p-value of 0. It will either be greater than 0.9999 or less than 0.0001. It turns out that we're not just interested in using the decision rule to fail or reject our null hypotheses. That's what our p-value has been used for. What we also want to know is that if we reject the null hypothesis, how sure are we of our observed results? So in the ECMO example, we rejected the null hypothesis and concluded that ECMO has a better survival rate than 0.44. But we observed 0.633. How sure are we, or how confident are we about that 0.633? Confidence intervals will give us a lower bound and an upper bound. So we will say we observed 0.633, and we are X% confident that it is really between this lower level and upper level. Confidence intervals, or CIs, allow us to actually make a statement about the population. So remember, we have tested 0.44. We have concluded that our sample is telling us that our population value is greater than 0.44. This is what's called inference. We have used our data to conclude that the survival rate with ECMO is greater than 0.44. And now we're going to use a confidence interval to give a range of values that reflect our certainty about the observed value of 63.3% survival. A few quick definitions. I just mentioned inference. Inference is a conclusion that patterns described in the data are present in our broader population. We sampled from the data, we used that sample to make a decision, and we're now going to use that decision to reference the population again. We're going to make some inference. A statistical inference is an inference justified by your probability model or your p-value. So we can make this inference back to our population because of our statistical test. Our parameter is that unknown value describing the feature of a distribution. That's our proportion here. We'll use means in the future. Our statistic, remember, is just a value that can be calculated from the observed data. That's our proportion, and our z-score can also be termed a statistic because we're using values from our data as well as values from the null hypothesis. And an estimate is a statistic used as a guess. That's our p-hat. That's our estimate of our proportion. The general definition of a confidence interval is our estimate, that's our p-hat, plus or minus. The minus will give us the lower bound, the plus will give us the upper bound. And we're going to add or subtract from our estimate a reliability coefficient times the standard error. Estimating this parameter with an interval involves our point estimate. Again, in this situation, that's our p-hat, or our observed value. We need the standard error of the estimate. So how much variability do we expect to be about our observed value? So remember, with confidence intervals, we're talking about our observations or our p-hat. And the reliability coefficient simply describes our degree of certainty, and it is based on that theoretical distribution. In our ECMO example, our p is 0.633. That's simply our 57 over 90. Remember, we're talking about the observed proportion here, so 0.633. The standard error we're using for confidence intervals is the standard error about p-hat. Recall earlier in our z-score, we used the standard deviation or standard error about p-naught. That was under our null. Here, we're not actually going to do the hypothesis test under the null hypothesis. We're actually estimating confidence based upon our observed data. So we're going to use the standard error associated with p-hat. If you recall the standard error of p-naught, it was p-naught, or our null proportion, times 1 minus p-naught divided by n, and you take the square root of that. All we'll do for the confidence interval is change p-naught to p-hat. So instead of SE p-naught, it will be SE of p-hat, and that's going to equal p-hat times 1 minus p-hat divided by n, and then take the square root. It's important to notice that the standard error of the estimate gets smaller as n gets larger. That's because we're dividing by a larger value. We'll expect less variability in an estimate if we use more data to make that estimate. That goes back to the sample size that we talked about, the n. The larger the n, the more secure you're going to be in your estimates. So if I study 10 people versus 1,000 people, I'll be more confident about my results from 1,000 people, and this is why. Your standard error is going to be smaller. You're going to have more oomph or more security when you use a larger n, more confidence. In the ECMO example, for 90, and then remember our p-hat is 0.633. The associated standard error is 0.0508. Now onto the reliability coefficient. This reflects how sure you want to be. Do you want to be 95% sure, 90% sure, 99% sure? Just remember that your confidence interval level should go with your alpha level. So if I'm testing at the 0.05, I should give a 95% confidence bound. These are all based on that underlying theoretical distribution. So for a two-sided test, if I was testing equal to or not equal to as my null hypothesis, I would put 2.5% of my alpha on one side, because it could be smaller than, or 2.5% of my alpha on the other side, because it could be greater than. So this would be for a test of equal to versus not equal to. If we were testing greater than versus less than, then all 0.5 or all 5% of our alpha would be over here. If we were testing to see if something was greater than, like in the ECMO situation, all 5% of our alpha would be over here on the right. And so instead of 1.96, we would see a 1.64. We are just using our alpha to look for things more extreme. So whether we're looking for something that is equal to versus not equal to, when our alpha is split up to both sides, looking for something that is smaller than, when our alpha will be on the negative side, or looking for something greater than, when our alpha will be on the positive side. All of our reliability coefficients will come from this standard normal curve when we're referencing the standard normal distribution. For 90% confidence, you would use a Z of 1.645. For 95% confidence, we would use a Z of 1.96. For 99% confidence, we would use a Z of 2.575. Our confidence bounds will always be two-sided. We're going to be looking for an estimate about the proportion, so it will be symmetric, lower than and higher than. The general formula for the confidence interval is our p hat plus or minus our reliability coefficient times the standard error of p hat. We already know that our p hat is 0.633. We know that our standard error is 0.0508. And because we want a two-sided confidence bound at the 95% level, we're using a reliability coefficient of 1.96. This gives us a lower bound of 0.533 and an upper bound of 0.733. You can see how 0.633 sits right in the middle. We observed 0.633. We're 95% confident that it's between 0.533 and 0.733. In other words, we're 95% confident that the survival proportion is between 53.3% and 73.3%. What do you notice? Our null hypothesis of 0.44 is not contained within that bound. 0.44 is way to the left of that lower bound. It's almost 9% or 10% below that lower bound. This indicates to us that not only did we statistically reject our null hypothesis in favor of the alternative, that our proportion is greater than 0.44, we observe 63.3 and we're 95% confident that the true proportion of survival from ECMO is between 53 and 73%. Is there a 100% confidence interval? For proportions, yes, it's 0 to 1. I am 100% confident that my survival proportion is between 0 and 1. That's a silly answer, doesn't make a conclusive statement about the population estimate. It would be the same for all proportions. It's nonsensical. We will use 95% confidence intervals more often than not, but you can have 90% or 95%. If we're using the 10 steps to report, we could state the question in terms of the confidence interval. We could decide on a summary statistic. That would be our confidence interval formula. Random variation actually assesses in the same way if the assumptions are met. If our null and p hat are very close, if our null proportion and observed proportion are very close, we would actually expect our confidence bound to include our null proportion. Step 6, we're going to determine the reliability coefficient. Usually, it's going to be associated with a 95% confidence interval. Step 7, we'll calculate the interval. Step 8, we'll compare the interval to the null value. So if there's a comparison value, does the interval include it? If the interval includes P0, then P and P0 are not different. Step 9, you could then state the substantive conclusion in terms of a confidence bound. And then step 10 would be document your understanding with the full text, including additional information about the observed survival and the N that you observed totally. So we've now looked at 2 methods to assess and describe data and underlying populations. We can use simulations, z-scores, p-values, or confidence intervals about an estimate to make conclusions about observed data, and then inferences back to our broader population. So remember, our z-scores and our p-values are simply going to test our null and alternative. Is our observed data what we expected to see under the null, or is it extreme enough for it to believe something new in the alternative? And the confidence interval then makes inference back to the population at large. So now that we have changed our mind and believe the alternative, what confidence do I have about my observed estimate? Coming up next, we'll have a section for you to read on your own about sample size and the precision of estimates. And then we'll continue on with testing proportions.